There is this truly frustrating paradox at the frontier of large language models right now.
Mhm.
You give a model a context window the size of a library, and you expect it to be this, super-powered archivist. You drop in 100 dense pages, and you just assume it will remember every single detail.
It should feel like upgrading from a tiny desk drawer to a massive
Yeah.
warehouse.
Yeah.
Right. But what happens instead is you move into this warehouse, you scatter your crucial documents everywhere.
Yeah.
And when you ask for specific detail, the model kind of goes, oh, I think I saw something like that maybe over there.
Exactly. The promise of infinite memory just hits a brick wall of diminishing returns. As those prompts get enormous, the model might technically see all the tokens, but its ability to reliably use them, to synthesize, to compare, it just plummets.
And this is the failure pattern that the research we're looking at is starting to formally call context rot.
Context rot. It's a great name for it.
It's insidious because it doesn't just, completely collapse. It's this slow, frustrating slide in accuracy. You ask it to aggregate data from 50 financial reports, and suddenly it misses a key constraint.
Or it hallucinates a total.
Or worse, it gives you a high-level summary when you explicitly ask for granular detail. The data was there, the model just couldn't keep it all salient.
So we have this fundamental crisis of scale and reliability. And the solution proposed by this research is, well, it's a brilliant conceptual shift. Recursive language models, or RLMs.
Right. They don't try to cram the whole document into the model's head.
Instead, they stop the model from swallowing the whole prompt. They put that massive input into an external environment, and they let the model interact with it programmatically.
And that core trick, turning the prompt from a limitation into an actionable object, that's what we need to map out. It's this prompt-as-environment bridge that connects long context agents, RAG, and memory into one, cohesive pattern.
Let's start right there, with the most impactful concepts. The sources are clear that RLMs are an inference time strategy. This isn't about retraining the model.
No, not at all. It's a new way of executing.
And the first pillar is what you just said, prompt as environment.
Think of it this way. A traditional LLM has to read a 500-page book in one sitting and then answer questions from memory. The RLM gets the same book, but for it, the book is a stable, searchable PDF file living outside of its working memory.
So it only pages in the tiny snippets it needs.
Exactly. This completely eliminates that quality tax you pay for having a massive input physically inside the attention window.
That is a huge mental shift. So instead of the input dictating the model's load, the model is dictating what input it wants to see.
Right, and that's made possible by the second pillar, the REPL loop.
The read evil print loop.
It's where the model really comes alive as an agent. It's a dedicated programming environment where the model writes and executes little bits of code Python commands, usually to inspect and slice up that external prompt object.
So you get incredibly cheap, fast I.O. Things like show me lines 300 to 350 or run a regex for the words liability.
Precisely. And that cheap I.O. saves the most expensive resource.
The reasoning tokens.
The reasoning tokens. You use the REPL loop to find the problem area, and only then do you engage the third pillar, recursive calls.
Oh, okay.
So when you need real, nuanced semantic work, the kind of thing regex can't handle, like classifying sentiment or pulling out a complex condition, that's when the model spawns a subquery.
On a much smaller piece of text.
It takes the snippet it just found, calls itself on that small chunk, and keeps the heavy reasoning local and focused. The result then gets stored back in the RPL environment for the main model to use.
This sounds brilliant, but I can also hear people thinking it sounds like a recipe for chaos, a never-ending chain of thought.
Which is why the fourth pillar they emphasize, budgets, is absolutely essential.
Right. This is the grown-up part of the system.
Definitely. Budgets, max depth, iterations, timeouts, caching, that's what makes an RLM production ready, not just some academic curiosity. Without those, you're running a stochastic process that could, as the source Riley puts it, spend your credit card on endless self-reflection.
You need those guardrails. Okay, so let's circle back to context rot itself. This RLM design is a direct response to it. Why exactly does a base LLM fail so badly as the context grows?
It really boils down to how the attention mechanism scales. It's quadratic, which means it tries to relate every token to every other token. When you hit 1 million tokens, the model is just overwhelmed trying to figure out which of those million are actually salient.
The signal-to-noise ratio just collapses.
It collapses. The model starts averaging out important details, reducing complex arguments into these generic, vague statements.
So if your task is to find, say, 50 scattered lines of evidence, aggregate them, and calculate a precise total, A traditional long context model might just miss one or two.
And it gives you an incorrect answer, but it says it with total confidence. That's context rot. The research shows this brutally. They tested base models like GPT-5 on these dense aggregation tasks, and the accuracy just falls off a cliff. But the RLM, because it's working on a stable external object and only processing small chunks semantically, it keeps that decision process sharp.
It's the difference between merely seeing the tokens and actually being able to use them reliably.
That's the core of it.
Before we get into the execution loop, let's just quickly clear up a naming thing. When you hear recursive language, a lot of people, especially from linguistics, will immediately think of Chomsky.
Right, and the structure of human grammar.
Yeah.
But here, the meaning is purely operational.
Like in programming.
Exactly. We're talking about the kind of recursion you'd write in Python. Solve a big problem by breaking it down into smaller, identical problems. The recursion is in the control loop that dictates how the model interacts with its environment.
That clarity is key. It really grounds this idea that the prompt is a symbolic object, not just a blob of tokens. So let's walk through the actual steps. How does this environment-based execution play out?
It's a 4-step cycle, and step 1 is just the setup, loading the context outside.
Huh.
The entire multi-million token document gets loaded into the REPL memory as a stable variable. Let's just call it document context.
And the main LLM, it doesn't even see that.
It sees the initial query and instructions on how to interact with document context. It might see 1,000 tokens of instructions, not 10 million tokens of data.
Okay, so then step 2, cheap I/O first.
Yeah.
This is the model making its first move.
Right. It generates simple code commands like document context.findall regex 2024 budget or slice 3000-3100. It runs these in the REPL. If it finds what it needs that way, great. It moves on. If not.
And we get to the actual reasoning part. Recursive calls for semantics.
This is the magic. Let's say the query is, what's the general sentiment on the Q3 budget cuts? A regex search might find 5 relevant paragraphs.
Okay.
The model then writes a specific prompt, wraps one of those paragraphs in it, and spawns a new recursive subcall, maybe to a smaller, cheaper model, asking just classify the sentiment of this paragraph.
And the result of that subcall gets stored back in the REPL.
For the root model to aggregate, that's the engine of reliable aggregation. You're breaking a huge task into lots of small, manageable, high-accuracy classifications.
And then the final step is just the stop condition.
Critical. The system has to know when to stop. It either gets the info it needs and spits out a final answer tag, or
It hits one of those budgets we talked about.
it hits the max depth, max iterations, or wall clock time. This makes the RLM a regulated stateful loop, not some open-ended agent.
This all sounds incredibly promising. But the real test is how it stacks up against what we're already using. RG retrieval, augmented generation, and compaction techniques.
Let's look at the competition. First, compaction and summarization. That approach is fundamentally lossy. It tries to squeeze a giant document into a smaller summary.
But it's assuming the details it throws away aren't critical.
Exactly. And for dense aggregation tasks, like calculating tax liability from 1,000 pages of policy, losing details means you're guaranteed to get an unreliable answer.
And RAG, it's fantastic for finding a needle in a haystack.
It is. RAG is a search paradigm. It shines with a narrow, focused question. But what if your task requires using 20 or 30 or 40 separate snippets of evidence?
The retrieval becomes a game of whack-a-mole.
Whack-a-mole is the perfect term. If your initial query doesn't perfectly hit all the scattered evidence points, your answer is incomplete. ARGI breaks because of those recall gaps.
So the RLM is for tasks where you need the completeness of a long context model, but the precision and reliability of something like RAG.
Exactly. The RLM changes the interface itself. It bridges that gap. The prompt isn't a token blob anymore. It's this massive, queryable object that the model manipulates with code.
So if we were to lay it all out, traditional long context models break with context rot. They're best for short, dense prompts.
Compaction breaks with lost details. Best for conversational continuity where precision isn't everything.
RAG breaks with recall gaps, so it's best for search-heavy Q&A.
Which leaves the RLM. Best for dense aggregation, massive documents, compliance reviews, complex code bases, anywhere you have to revisit details repeatedly without approximation.
And its failure mode is the control loop tail risk.
Right. You might hit your budget limit before you find the answer, but that is a much more predictable and controllable failure than just getting a silently wrong answer from context rot.
That brings up the natural objection, though. Isn't this just a complex sub-agent framework? Aren't people already building agents that use tools and loops?
They are, but the authors point out two really crucial differences that make the RLM paradigm distinct. The first is what they call the boundary.
The boundary.
Most agent systems still keep the prompt at their center of gravity. The model is constantly trying to manage ingesting and remembering that huge input, even while it's using tools. RLMs flip this. The prompt is stable, it's outside, and it's inspected purely on demand.
And the second difference is about a core design assumption.
Right. Compaction assumes forgetting is okay. RG assumes search will be good enough. RLMs are built for the exact opposite. For cases where you must revisit details over and over to ensure precision, it's a system built for meticulousness.
Okay, let's get to the numbers. The claims in the paper are pretty significant. They talk about handling inputs that are 2 orders of magnitude 100 times larger than the model's native context window. How did they actually prove that?
They used a benchmark called OOLONG, and it's specifically designed to stress test dense aggregation semantic transforms over chunks, and then aggregation over nearly all of them.
The exact failure mode for base models.
The exact failure mode, and on a task called OOLONG pairs, which requires almost quadratic work. The results are, well, they're remarkable. The base model scored essentially 0. The RLM, with its structured approach, hit 58.0 F1.
And F1 is a score that balances precision and recall.
Meaning the RLM was reliably extracting and synthesizing the correct information. It really shows that the scaffolding keeps the model upright when the base model just collapses under the weight.
Now, let's talk cost, because this is where the skeptical listener is going to raise an eyebrow. Doesn't adding a complex control loop and all these subcalls make it prohibitively expensive?
That's the core tension, you're right. You're doing more steps, but you're using a tiny fraction of the expensive reasoning tokens per step.
Right.
So they found the average RLM cost for handling these huge inputs, we're talking 6 to 11 million tokens, was around 99 cents. The theoretical cost of just trying to ingest that directly and unreliably was estimated between $1.50 and $2.75.
So you get higher reliability and potentially lower median cost. But we have to come back to that elephant in the room, the cost tail, that risk of the control loop spinning out.
This is the primary trade-off. Reliability is bought by introducing a control loop, and loops can create long, expensive trajectories. This is exactly why the budgets we mentioned earlier are non-negotiable.
The essential safety nets. So let's just drill down on those 3.
First, the iteration budget. That's a hard cap on how many REPL steps the model can execute. Then, the recursion budget, which dictates max depth and the total number of subcalls.
And the final one.
The time budget. A simple wall clock timeout. If the RLM is churning away for 3 minutes, the system just kills the loop and returns the best partial answer it has. It keeps the whole process commercially viable.
So for the listener who's thinking about actually deploying this, where does this pattern best apply?
You should treat it as a pattern, not a universal fix. Use it when the input is huge and dense, and you need that meticulous aggregation. Think giant legal policy documents, complex code-based analysis.
Any workflow where you have to compute, not just approximate.
Exactly. Avoid it for simple creative prompts or short, straightforward summarization.
And they offer a clever cost trick, too. The pick-2 model strategy.
Oh, this is absolutely essential for production. You pick a powerful, strong root model, like a high-tier, large model for the high-level planning and decision-making. But then you use a cheaper, faster, smaller model for all the recursive subcalls.
For the small semantic chunks.
Right. It maximizes your capability-cost trade-off.
This whole approach feels like it was built to slot right into modern agent orchestration frameworks. Is that where the authors see it fitting?
Yes, absolutely. Think of an agent router. The router decides if a request needs search, which would be RAG, or code execution, or context management. The RLM becomes the specialist for context management.
So the router sends the request, and the RLM takes over with its internal loop to inspect the prompt.
And that's how you get stable, repeatable control over these huge inputs inside a bigger agent system.
Looking ahead, what are the current limits? They mentioned that synchronous subcalls can introduce latency.
That's a known bottleneck. The main model has to wait for the smaller one to finish. They also acknowledge they rarely went beyond a recursion depth of 1 in their experiments.
So deeper, more complex recursion is still an open area.
It's a natural next axis to explore. And the final step is maybe the most exciting. Actually training models specifically to be exceptional decision makers over this kind of external environment. That would make the whole loop far more efficient.
This whole discussion really does reframe how we look at LLM memory. We've learned that recursive language models turn the context from a constraining blob of tokens into an actionable, stable object, one that the model can programmatically inspect to prevent the unreliability of context rot.
The takeaway isn't just academic, it's practical. This architecture shifts the responsibility for context management away from the model's fragile internal attention and onto an external, predictable control loop.
So here's the challenge for you, the listener. Pick one specific information-dense task in your existing pipeline, something where you use RAG or a long context LLM, and you secretly distrust the answer. You suspect it might have missed a detail.
And then wrap that specific task in a minimal harness, a tiny REPL loop implementation that can peek, slice, and then call a submodel for the semantic chunks. Give it those crucial budgets, log the trajectory, and then just compare the output to your base model.
The final takeaway is this. If that minimal harness works and the answer is suddenly reliable, you've just upgraded your interface between language models and reality. And if it fails, you learn exactly where your existing pipeline leaks, which gives you a clear, structural path to actually fixing the problem.